I'm Nikita Dakulkar, and this is my lab for Physics 2211, Lab 2, Motion of a Falling Object. The purpose of this lab was to use Newton's laws of motion in the real world by tracking the falling motion of an object, in this case, an empty pencil pouch. The actual position versus time using tracker software was compared to two different models, one that only accounted for gravitational force and one that accounted for both gravitational force and drag force. We will see that the one using both forces was more accurate to the real-world data than the one only using one force. The first fundamental principle is Newton's second law, which relates the net force between a system and its surroundings and the observed motion of that system. In this case, the motion is non-constant, so the net force does not equal zero. The net force is also equal to the change in momentum over the change in time, and momentum is, of course, just mass times velocity. The other two fundamental principles used in this lab are gravitational force and drag force. Gravitational force is the force exerted on the object by the Earth that pulls the object towards the Earth. It's represented by the formula F equals negative mg, negative course being the direction vector down. Drag force is the force that is exerted on the object by all the different particles in the atmosphere that the object comes into contact with while it's falling. So the bigger the object, more particles, larger the drag force. It's represented by the equation F equals negative b, the magnitude of v squared, times v hat, the direction vector. B is a constant. So let's clarify some initial conditions. The system would be simply the falling object, in this case just an empty pencil pouch. The surroundings would be everything else in the universe. Me, the atmosphere, the Earth, everything. The initial position in this case is 0.00459 meters in the y direction, with the x and z directions being 0, and the initial velocity in this case is all 0 meters per second as well, since the object is initially starting from rest. So, the actual observed data. I took a video of myself dropping the pencil pouch, then uploaded that video onto the tracker software. This software was then used to track the position of the pencil pouch over time. This was done in increments of 0.033 seconds because that was the frame rate on my phone. The total amount of time it took for the object to hit the ground was 0.6 seconds, so that's our total change in time. The data for the time versus the position, specifically in the y direction, was then uploaded onto Excel for further data analysis. The first computational model only took into account the gravitational force. I took a starter code and edited it on GlowScript. The mass of the pencil pouch was measured to be 0.067 kilograms. The initial position of the vector was found using the tracking software, and the initial velocity was found to be 0, 0, 0. Remember, because the object's at rest. The delta t was set to be 0.033 seconds, so that's the frame rate on my phone, and nothing else in the initial conditions was changed. On the right-hand side is the calculation loop. T was changed to 0.6 because that's how fast it took for the pencil pouch to hit the ground. I had to add the formula for the force due to gravity using the gravity force formula mentioned earlier, and the gravity force would be equal to the total net force. Finally, the velocity and the position of the pencil pouch was updated during every iteration using the velocity update formulas and the position update formulas. This program was run to find the data for the computational model using only gravitational force. The second computational model included both the gravitational force and the drag force. The only thing changed in the initial conditions this time was b, the proportionality constant. This was found using guess and check by just changing the value of b, then running the program and seeing what value of b was needed to get as close as possible to the final position vector found using the tracking software. Then in the calculation loop, we had to add the force due to drag, which is found using the drag force formula. Norm Bovril is just the v hat vector, and then F net now equals the force of gravity plus the force of drag, not just the force of gravity. This program was then run to find the data for the computational model for gravitational force and drag force. So here is the data for all three models. As you can see, the velocity of the model with gravity, which would be dark blue, increases at a much faster rate than both the tracker data and the model with gravity and the drag force, which are brown and teal respectively. This is because that the model with gravity doesn't take into account any real-world drag forces that oppose the gravity. However, the model with gravity and drag force as the net force does mimic the real-world data and is much more accurate. Terminal velocity is the velocity a falling object reaches when its drag force is equal to its gravitational force, so the net force is 0. This is shown by the model that uses both gravitational force and drag force, because drag force has to be present for terminal velocity to be reached. If it was thrown downward, the terminal velocity would still be reached, it would just be reached faster. This is shown by the graph made by the tracking software in which the terminal velocity means that the slope of the velocity versus time graph evens out.